question 19, and I'll try to do it in one take, and hopefully it works out. You'll know by the end if it's actually done in one take or not. Okay. So I'm not proving question 1, 2, and 3 because I already did in the theory portion. So let's jump to question 4. Okay. So I'll just write the definitions and then the homeomorphism will be clear. Note that we already did define the bijective correspondence between the two sets in section 5. So yeah, let's see. So we have a function and then another function, and then it's mapped to a function. Yeah. And this is the function, sorry, it's a set of functions. Sorry, so I'll just call it this way, I guess. Yeah. Actually, yeah, we're mapping functions, so I guess, yeah. Where this was the map, and these are all members of the things that are being mapped. So not much more to discuss. Yeah. And here we have the set of all functions from x, so x bar from 1 to n minus 1, right? Yeah. So that's the index set, and it goes to x. Is the same set, right? It's is it even mentioned? Okay, it's not completely clear whether they're indexes of the same set or x alpha happens to be different here. So we have to check that. But let's say, yeah, I'll pretend it's the usual definition. So x here refers to union I is equal to 1 to n xi, right? And it's the usual, x belongs to xi case. I'll take that case because even if xi happens to be the same, then the union just happens to equal x. So we're safe in either case. And g is just the identity function. It's just yeah. So we don't really need to care much about g. In fact, we can even replace g by a member x itself, xn, if you want. So because of the bijective correspondence. So if you replace it, g, which is a function from singleton 1 to x or xn, it doesn't matter which you take. So yeah. Now we have to define a function from f and g. So I'm actually attempting that question from section 5 again, essentially. Yeah. So h of I is equal to f of I if I is less than n and is equal to g of I or xn otherwise. Now, is this a bijective correspondence? I'm not doing that again. It is. And is it a homeomorphism? That's the real question. Yeah. So an open set in H in the other, so an open set would be what? It would be a set of functions that, make up, pi un or ui. Yeah. And the inverse image, so because I'm not going too much into it, but the inverse image, H inverse. Oh, sorry, this is not the entire map. Okay, I'm going to call this G. I'm going to call this G, and I'm going to call this H. H inverse of this basis element. Note that since the selection is finite, we don't care whether it's box or product, the topology, right? Yeah. So what's the inverse image going to be? Mm, yeah. So we're going to have un, and then pi I is equal to 1 to n minus 1, un minus un I. Yeah. And note that this is open because this is open, and therefore the entire product is open. So yeah. And the same thing backwards. If these two are open, then the inverse image. So because it's a bijective function, the inverse images are just, they're going to look nice. And yeah, they do. So this will turn out to be ui pi I is equal to 1 to n. So yeah, the forwards, this function's, the inverse function's inverse image. So yeah. Yeah, so they're homomorphic. If you want to get into the, nitty-gritty of the proof, just you have to check about, them being open functions. them being essentially sets of functions, right? But yeah, open sets turn into open sets. It's a kind of identity. This part will be shown through the, yeah, you have to, you'll have to use the definition quite rigorously, and I don't really want to get in. Essentially, whatever intuition you have with regarding products, it's not violated that much except for the product and box topology thing. That's pretty much the only amount to which your intuition is violated. So I've technically also solved question 5. I'll just say it again. So we showed that the f implies f alpha 1 is trivial and does not rely on the box topology at all because phi alpha is a continuous function, right? And the other one, we had a counterexample. So yeah, only one of them applies. Yeah. Okay. Let R alpha infinity be the subset that is eventually zero. Subsets of points that are eventually zero. Yeah. So I proved it earlier, but I'll say it now again that if a topology is finer, then the closure will be smaller. And that's because you have more you have more closed sets to intersect from, and you also have more open. You have so you know that there exists U, right? We have that for the lemma. We have more open sets to use as eliminators for points, and that's why a finer topology will have a smaller closure. So yeah, that's not going to help us much because we ultimately need to determine the exact closure. And yeah, let's do that. Okay, so yeah, so in the product topology, uh, the closure of R infinity is actually completely R omega. And why is that? Let's see. So R infinity, any point from R infinity is obviously going to lie in the closure trivially. Now let X not belong to R infinity, but belong to R omega, right? Right. So yeah, so let U V be a neighborhood of X, right? So this V is going to have a basis element, and that basis element is going to be a finite intersection of subbasis elements, right? So it's going to be what? Let's call it alpha 1, U1, and intersection. Yeah, yeah. So an finite intersection of basis elements, and that's and this is going to be contained in V, right? Okay. Now this is going to intersect. Okay, so X doesn't belong here. Yeah. So if we identify any point of R omega that X of R infinity that this neighborhood intersects with, since this neighborhood is arbitrary, uh, X will then have to belong to the closure, right? Yeah. Okay. So essentially, I'm testing that if X belongs to R omega, then X belongs to R infinity closure by using the lemma. All right. So how do we do this? Yeah. So so I'm going to name a point in R infinity that does lie. Okay. So for all alpha I, X of alpha I is equal to, okay, I'm going to call that point Y. So Y belongs to V intersection R infinity. So let's define this point Y. Y alpha I is going to be equal to X of alpha I. So it's the same for all alpha I. And otherwise, Y beta is equal to 0. So it's equal in only these points. Note we're exploiting the finiteness of the product topology here, and it's going to be 0 otherwise. And note that this is precisely a point that belongs to R infinity as well, and in the neighborhood. So because of that, the closure is R omega. But in the box topology, we don't have that. And why is that? So in the box topology, we have to approach in the opposite way. We have to show that any y in, let's see, R omega and that's not in R infinity, y does not belong to R infinity closure. So that means we need to identify a neighborhood that doesn't intersect it, and that's pretty easy. So yeah, because the standard topology is Hausdorff, we can always find a disjoint neighborhood, right? We can always find a neighborhood B that's disjoint from the point 0. We can actually have two neighborhoods separating it, but we don't need that here. We just need, the separation. And that's precisely what we're going to exploit. So since at every point we can have this disjoint neighborhood, we're going to have that at infinite points. And therefore, this neighborhood, we found a neighborhood of y that's in R infinity. Sorry, x that's in R infinity. Sorry, x that's in this y. So, okay, sorry. Yeah. The y will not be in R infinity and in R omega. And we will have found a neighborhood that doesn't intersect 0 at infinitely many points, right? From the Hausdorff condition. And it can because y is not in R by assumption. So now what now? Yeah, I think we found an open set in the box topology that eliminates every other point of R infinity. Am I missing anything at all? No, we use the Hausdorff property of the standard topology here, and yeah, so the eventually zero, right? It's only not zero for finitely many. So it has to be zero for infinitely many values, and yeah, so it's fine. Okay, let's show that a product of an infinite product of linear transformations is also homeomorphic. Okay, so AI is greater than zero for all I. So if I show that the maps are actually order preserving, then we're done, right? So let x, so we're studying an x alpha here, the x alpha or xi if you want. Yeah. And let x not equal to y. So let x less than y. So since AI is positive, AI of x is less than AI of y from section 4. So you can check all the laws there. And since bi is a constant, AI x plus bi is less than AI x, y plus bi. And note that all of these steps are f and only f's. And from that we get that this map is an order preserving bijection. The bijection also follows from the so the injectivity follows from the fact that it's order preserving, and the surjection follows from for any point on a line you can, for any real number you can get a point that matches it on the line, and that's because AI is greater than zero. It's not constant. If it's constant, then we have a problem, but since it's not constant, we have some line. So it's a homeomorphism at every stage. Now the question is it going to be a homeomorphism at the complete stage, right? Yeah. So I think it will be. So we have two product topologies and yeah, with itself, yeah. Okay, so pi inverse alpha of u alpha, right? What is the inverse map going to send it? So R will just go to R and this will go to some open set. So it's going to be open in the product. So in the product topology, oh, actually, yeah, note that. So this is a continuous map because it's order preserving. It's an order preserving bijection. And note that the inverse map is also something like that. So we'll have minus pi and then 1 by ai or something like that. This map is also satisfying the same category. So the inverse map is also continuous, and because of that, you just have to prove it in one direction. Yeah, so the pi inverse here is going to be, oh, sorry, this is the surface. Yeah, essentially it's going to be nice because at every point we have the inverse image behave exactly how we want. Because Yeah, it's homeomorphic at every point. The homeomorphisms are quite off. So yeah. Hmm. Okay, I'll take a break. Yeah, so it did not happen in one take. Let's solve question 9 now. So I think question 8 can be generalized to like if you have a set of homeomorphisms, for each space, but I'm not going to do that. Yeah, let's see. So choice is equivalent to that one. So yeah, it's another equivalence and you haven't seen it in a while. Yeah. So I'll prove this one first because it seems more interesting. Yeah, so the biggest problem here is that we don't actually have an index set, right? And what I'm going to do is I'm going to take the set itself. So for choice, we have a collection of whatever alpha, and we need to find a choice function on it, right? So for each, let's see, it goes from alpha to union of alpha. Yeah. Okay. So and such that C of A belongs to A, right? So all of this looks very familiar, and the thing is, yeah, the choice function and the choice function is an example of the a function in the product topology. Sorry, in the product space. Yeah. So we have an index set alpha, right? And we have so calligraphic A, I'm going to call it alpha, whatever. And we have a collection of not necessarily disjoint sets or even disjoint doesn't matter. And yeah, now yeah, we have so to get this, we're using any member from the product space. So this is going to serve as our choice function. And why is that? Well, yeah, we have an indexing set, which is the set itself, and note that it is an indexing set because for every member we can just use the identity function, and the identity function is always a bijective function and therefore surjective. So yeah, it serves as an indexing function as an index set, and by definition, every x alpha is going to belong to a alpha, right? So yeah, we just write C of A alpha, doesn't really matter here, but we're taking A alpha as X alpha. And yeah, it goes both ways, essentially. This choice function will give us the single element in the product, in the Cartesian product. Sorry, I said product space. Yeah. So yeah, it goes both ways. Okay. Yes, let's solve question 10 now. Um, yeah, so show that there's a coherence topology. Question part B is actually the hint for it. So taking union of, you know, pi inverse beta u beta, right? So it's not pi inverse. Yeah. So if the topology is defined on open set such that these are defined to be open, then it's going to end up being continuous, right? So yeah, hang on, yeah, this and yeah, u beta is open in X. Yeah. So the reason this works out is first of all it's a subbasis because you take the inverse image with respect to two different open sets, right? You'll get so two different coordinates are meant, yeah, x alpha and x beta. Alpha is not equal to beta. So you take the image. Hmm, okay, let's see. So actually, yeah, if the whole space is there, then we're done, right? Yeah, so X alpha is an open set, and F inverse of X alpha is going to be the whole set. So we're defining the whole set as open. So we're done, right? Yeah, since X alpha must contain the range of A. So because of that, uh, yeah, it's a subbasis because of that, because it contains the entire space. Its union contains the entire. So it's a subbasis, and it's fine. Under from the topology generated under this subbasis, it's going to be every function is going to be continuous because we're literally including open sets that are just continuous that way, and their finite intersections are going to be continuous because well, let's see. Okay, so why would any finite intersection of these be continuous? So I'm solving A and B, but simultaneously, right? Let's go. Okay, so this would be open essentially. That's what you have to show, right? Actually, yeah. What am I doing? It doesn't matter. So we're defining it to be open because it's a basis element. So yeah, nothing. I was being stupid. You take an open set in XP and then you take its inverse image and then you call it open. That's how you define it. So any topology that happens to satisfy the criteria that every F alpha is continuous would have to contain these sets by definition. So yeah, and this so it, every you just take the intersection and then you can get the course's topology and note that the intersection is a topology, so we don't have to worry much. And yeah, we even identified its subbasis. So note that this isn't a product topology. We're getting a topology from a product. Okay, so show that G from Y to A is continuous if and only if GO F is continuous. And F is, oh, do we have another part before this? Oh, F each alpha. Oh, yeah. If each map F alpha OG is continuous. Okay. Okay, let's see. So any open set here will be of the form F inverse essentially. Yeah. Okay, so we take any arbitrary open set in the product topology, right? Now, any open set here is going to be of the form of, it's going to be generated from the subbasis here, right? Yeah. So let's see. G inverse of F alpha inverse of U. So this map is, yeah, okay. So U alpha. So U alpha is going to end up being an open set in X alpha, right? So because this map goes from Y to X, yeah, X alpha. Okay, so this is trivially continuous because this is a continuous function and this is a continuous function, so it's a composition. So one direction is trivial. Now for the other direction, yeah, so we have an open set here, right? And this is given to us as continuous, and this is what has to be determined to be continuous, right? Yeah. But note that this is a subbasis element. So the inverse of a subbasis element is given to for any arbitrary subbasis element is given to us to be continuous. So this is identical to the proof of 90 points. Any arbitrary subbasis element is given to be continuous. Its inverse image is given. So even that direction. So, yeah. Okay, now we're defining a new map. Yeah. F from A to Z, right? And we have to show that this is continuous. So yeah, Z is equal to F of A. And sorry, F is equal to F of A, F alpha of A, alpha belongs to J. Yeah. So it's a tuple, sorry. Yeah. So let's see. Okay. So what would so it's a subset of the product space, that's for sure. It's a product worthy, right? Yeah, product space, yeah. And also by default assume the product space is not mentioned. So yeah. We just need to check that its subbasis gives us an inverse image, right? So its subbasis would look something like pi inverse alpha, what, u alpha? U alpha is open in X alpha. So yeah, note that, oh wait, we don't have to show it's continuous, right? Yeah, sorry, my bad. Okay, so take any open set here, U alpha, right? U. It's hmm. So U is made up of so unions. We don't really have to worry about them at all because unions can go in and out of the functions, right? Unions can go in and out, and containment can go in and out, right? Section 2. So we just have to worry about intersections. So I'm going to call F any open. So we just need to check for basis elements is what I'm saying. So let's check for basis elements to, yeah, F alpha 1 inverse of U. Yeah, yeah. So we need to check that this is open, right? Okay. So what is F of this? It would end up being okay. So we can at least confirm that this is open because it's going to contain the whole set, the whole range, right? And the whole range, by the definition of the subspace and any topology, is going to be open. So we're getting the whole space A alpha producted with, yeah, so this is the whole space, except if it's alpha 1. If alpha is equal to alpha 1, then it's going to equal to U. Then, and otherwise it's the whole space, so A alpha. So that's what we're going to get with this intersection. And yeah, with the other intersections, we're going to get a similar open set. So what's going to happen? We're going to get, actually, it's not U, is it? It's going to be F alpha of U, I guess. Yeah. Yeah, I guess it's F alpha of U. But note that this is designed to be an open set since U is made from F alpha, the inverse of F alpha. So it's going to be an open set. And yeah, for the other cases, it's the whole set, so it's also going to be open. And with the intersections, you're just going to get them at finite stages. So yeah, they're going to be open in the product topology, and I'm not writing a detailed proof. That's the intuition. So yeah. Oh, we're done. Okay.